Sometimes the most powerful tools aren't the ones they teach you in class. They're the ones you find on your own. For young Richard Feynman, one of these tools felt like a secret weapon, a kind of mathematical cheat code he stumbled upon. So the story goes, his high school physics teacher gave him an advanced calculus book just to keep him busy. And inside, Feynman found this peculiar way to solve integrals. And this one technique let him crack problems that left his super smart classmates at MIT and Princeton totally stumped. So what was this thing? What was the secret weapon that gave one of the greatest minds of the 20th century such a huge advantage? Well, let's pull back the curtain and take a look. All right, let's get right to it. We're going to break down Feynman's favorite trick. It's got a pretty formal name, but the idea behind it is actually surprisingly creative. Okay, so officially it's called differentiation under the integral sign. I know, that sounds like a total mouthful, but forget the name for a second and just think about the process. You take a really hard problem, you add a new variable to it, then you differentiate. And that one move magically simplifies the whole thing. You solve the now easy problem, and then you just integrate back to get the answer to the original tough one. It's this beautiful, roundabout way to find a solution. So here's the key idea. This trick isn't just about crunching numbers. It's about transformation. It turns a frustrating brick wall you can't get past into a creative puzzle that you can actually solve. Look, the best way to really get this is to see it in action. So let's walk through a classic Hello World example of the trick. We'll go step by step. So, here's our game plan. It's a simple, four-step process. We start with a stubborn problem, we introduce a new variable to make it more flexible, we hit it with that magic differentiation step to simplify it, and then we integrate back to get our answer. All right, here's our opponent. Now, at first glance, it doesn't look too terrible, right? But that natural log of x down in the denominator, oh, that makes it an absolute nightmare. With standard methods, you're just stuck. It's a dead end. And now for the clever move. We introduce the parameter t, and we just stick it in there as an exponent on the x. And here's the beautiful part. If we set t equal to 1, we get our original problem right back. So we haven't actually broken anything. We've just turned one rigid problem into a whole family of flexible ones. And this is the payoff. We differentiate the whole thing, not with respect to x, but with respect to our new friend, t. And when we do that, something incredible happens. That pesky logarithm in the denominator, it gets canceled out completely. It just vanishes. And we're left with an integral that's so much simpler. It just becomes 1 over t plus 1. We are in the home stretch. We used a derivative to break the problem down, so to build it back up and get our answer, we just do the opposite. We integrate. We take that super simple result and integrate it with respect to t from 0 up to 1, since our goal was to find the answer when t equals 1. And there it is. The answer to that impossible-looking integral is just the natural log of 2, an elegant solution we found by turning the problem into a much easier puzzle. Pretty cool, right? Now, that all seems pretty amazing. But I know what you're probably thinking. How in the world did we know where to put that parameter t in the first place? And that, right there, is the million-dollar question. This is where the trick stops being a simple recipe and starts becoming a real art form. Where you place that parameter, it's everything. So check this out. For the same problem, you could try putting a parameter in different spots. The choice on the left? That's a dead end. Differentiating it just makes a bigger mess. But the choice on the right? Putting b inside the function? That's the key. When you differentiate that, it creates a simplification that cracks the whole thing wide open. So here's the rule of thumb. Find the part of the integral that's causing all the pain. Find the roadblock. Your goal is to place the parameter in just the right spot so that when you differentiate, you eliminate that roadblock. You always want to make the problem easier, not harder. Okay, so once you've got the basic move down, there's a serious upgrade. Think of it like a power-up that can handle even nastier problems. Yeah, sometimes you don't even add a parameter. You do something, well, kind of wild. You take a whole chunk of your problem, like the term 1 over x, and you replace it with a different mathematical expression that you happen to know is its equivalent, an integral. It's like swapping one piece of an engine for a completely different pre-built system. It looks more complicated at first, but it can totally change the game. Take this very famous integral, sine of x over x. Using this method, we swap out that tricky 1 over x term. Now, yeah, this creates a scary-looking double integral, but here's the key. You're allowed to swap the order you solve them in, and when you do that, the inside integral becomes surprisingly easy, and what you're left with is a standard problem with a well-known answer. And the result?
The beautiful and famous answer, pi over 2. It's just another, more powerful, example of the same core idea, transforming a problem you can't solve into one that you can.
So after all this math, what's the real lesson? Let's bring it all the way back to where we started, with Richard Feynman himself.
He said he got this incredible reputation not because he was necessarily smarter, but because his box of tools was different. Everyone else was hammering away with the same wrenches they learned in school. Feynman showed up with something completely new.
And that is the ultimate takeaway. The cheat code isn't this one specific trick. It's the mindset behind it. It's about being curious, looking at a problem and saying, what if I don't do it the normal way? It's about building your own unique box of tools.
So I'll leave you with this question to think about. Whether it's in math, at your job, or just in your daily life, what seemingly impossible problems are you facing right now that might just be waiting for a different set of tools?